Hello, this is John Noguera. I am the Chief Technology Officer at SigmaXL to present the new features, the new templates that are in SigmaXL version 6.2. Our agenda for today, we'll talk about the new templates. First, it's compatible now with Excel 2013, both 32 and 64-bit, as well as the Mac Excel 2011. The new templates that we have include a minimum sample size for robust T-tests and ANOVA, one Poisson Rate test, two Poisson Rates test, and a one-way chi-square goodness of fit test. We've also updated the templates Onesample T, Twosample T, Onesample chi-square test for standard Div, Twosample Ttest, and 1 and 2 proportions have been updated. Just by way of introduction to the minimum sample size for robust T-tests, that template answers the question, how large does a sample size have to be for a T-test to be robust to the assumption of normality? And it's often said that you use a sample size of 30, but that really depends on what your skewness and kurtosis are and exactly what type of test are you doing. For example, if you do a one-sided one-sample T-test, the requirements are quite different from a two-sided one-sample T-test, and we'll look at that. We did extensive Monte Carlo simulations to come up with answers so that you just dial up the test and enter the skewness and kurtosis, and then we give you the minimum sample size. Another thing we've added is just easier to interpret, very clear, reject or fail to reject the null hypothesis. The new features in the templates, in the one proportion test, we have both the test and the confidence interval. And I just want to comment briefly, when you're dealing with a binomial proportion or a Poisson rate, the problem that you have is, unlike a continuous, for example, the confidence interval for a T-test, where when you say you have 95% confidence, that confidence is true when you're doing the test, regardless of the conditions. When you have a discrete test, like the one proportion, you have what's called an oscillation. And I have here, for example, an exact confidence interval. And as the proportion changes, this is for a fixed sample size of 50, what you can see here is that the actual true coverage varies all over the place. So first of all, it starts off at around 99%, and then it drops here, and then kind of oscillates down, and then oscillates back up again. And by definition, when we say an exact confidence interval, what it means is that it guarantees that the minimum coverage is going to be 95%. What that translates to in confidence intervals is, unfortunately, that conservative interval is unnecessarily wide. So there are other confidence intervals that we've added, and one of them, for example, is called the Wilson interval. On average, you get your 95% coverage. So again, there's oscillation, and it can dip quite a bit as you get close to 0 and 1, but on average, you get 95% confidence interval. What that actually translates to in practice is that you have narrower confidence intervals. So it's essentially a more powerful confidence interval. We'll cover that as we get into the details. So we'll look at the one proportion, two proportions. This is actually going to be a brief presentation because all I'm going to do is just touch upon the various templates, kind of quickly walk through them. We'll switch over to the templates. The location of the templates under Templates and Calculators, Basic Statistical Templates, or under Statistical Tools, Basic Statistical Templates. So all the new templates are here under Basic Statistical Templates. I'm not going to touch upon the templates that haven't changed. I'm only going to talk about those that either the new templates or the ones that have been modified. Minimum sample size for robust hypothesis testing. The default settings here, you enter your hypothesis test, a one-sample t-test. You enter your alternative hypothesis, so not equal to. So this is a two-sided test or a two-tailed test. Confidence interval, 95%. I'm just going to say that I happen to know, I collected some data and I measured my skewness and kurtosis, and it turns out the skewness is 1 and the kurtosis is a negative 0.48. You could just use descriptive statistics, right? Under descriptive statistics on your data, that will give you the skewness and kurtosis values. So that's where you would get skewness and kurtosis from the descriptive statistics. Now, the calculator is telling me that you need 30. And so you can say, well, right, that's the rule of thumb, 30. So why do I need the calculator? It is validating. The calculator is validating this particular condition or this particular test of one-sample t-test with a moderate skewness. A moderate skewness is a skewness of 1. A severe skewness is a skewness of 2. And extreme skewness is a skewness of 5. Now what I want to do is I just want to throw in some, maybe a different example here. Let's change this problem. We'll keep it a one-sample t-test. Let's turn this into a one-sided problem. So let's change that to less than. So you can just select from the drop-down list. And let's say we want 99% confidence. All right, so we're going to select 99%. The sample size now is 752. All of a sudden, that rule of thumb is no longer a very useful rule of thumb. So if I have a one-sided, one-sample t-test with a 99% confidence interval, I need a much bigger sample size to guarantee robustness. Now, you might ask, well, what do you mean by robustness? And in our notes here, robustness is defined as being within 20% of the specified alpha value. Okay, so if in this case, I have an alpha value of 0.01, what I do is we run simulations with a specified skewness and kurtosis, and then just keep increasing the sample size till it gets to the point where the alpha value or the observed alpha value is within 20% of the specified. That's just a technical note, but the point is, and also another side note is that power is not considered here. Okay, this is not a power and sample size calculator. Those are in separate place in SigmaXL. But what this does is this answers the question, what sample size do I need if I have non-normal data to ensure that my t-test is still going to give reasonable results? And under the ordinary circumstances of a moderate skewness of 1 in a one-sample t-test and two-sided, we saw it was 30. But now, a one-sided t-test with a 99% confidence level, we need a much, much bigger sample size. Now, in this case, practically, you would have to go to a non-parametric, all right? So you would have to go to like a one-sample sine or a one-sample Wilcoxon rather than the one-sample t-test. So that's also an important understanding on the use of this template is it's essentially telling you when it's okay to use the one-sample t-test and when you need to switch over to the non-parametric. And the non-parametrics are all down here under SigmaXL tools, non-parametric tests. All right, they're robust tests that use the medians and do not assume a normal distribution. So it's all based on central limit theorem. And the larger the sample size, the more robust is the test. But sometimes, however, it can go the other direction, which is area is actually more than you need. So the ANOVA, for example, is quite a robust test. So I'm going to change the test to a one-way ANOVA. So I just use a 3-sample or a 3-group one-way ANOVA, and we'll make this a two-side, change it to not equal to, and we'll go back to 95%. Now, n is equal to 3, okay? And by the way, these are all based on regression models that were developed, again, using Monte Carlo simulations. The regression models are actually all given here, but these are just, unimportant as far as the user is concerned, but if you're interested in what the formulas are, they're all here. You can see that n is equal to 3. So if I am doing a one-way ANOVA and I have moderate skewness, even a sample as small as 3, that's per group, is sufficient. So the ANOVA is really quite a robust test. Let's put in like a crazy number, like 5. 5 is like a huge skewness, and it's only 70 now. If I have 70 per group with a very large or an extreme skewness of 5, I'm still going to be okay. So this template allows you to choose from Onesample T, Twosample T, and the ANOVA, one-sided, two-sided, different confidence levels. It gives you that minimum sample size. So from a teaching tool point of view, or just trying to understand, is it safe to use the Onesample Ttest, you can use this calculator. And it also just helps to give you a feel for just how robust are the tests. That's all I'm going to say on the minimum sample size for robust hypothesis testing. In the workbook, in the SigmaXL workbook, we include reference papers as well, other papers that have been published on the topic of robust hypothesis testing and minimum sample size and so forth. So you can see that our work is building upon other people's work. But what we did here was, with these Monte Carlo simulations, put it all together into a template so that it's easy to use. Now let's switch over to the Onesample basic statistical templates, and let's have a look at the Onesample Ttest. Now the old templates, there's a lot of similarity here, but one of the things that we've added is in the old templates we reported all the p-values for less than, not equal to, and greater than. And this just cleans it up. It's actually more consistent with the menu-based Onesample Ttest. Here you enter your summary statistics, your hypothesized mean, and I can change my alternative hypothesis. And notice that when I change this from a two-sided to a one-sided, the p-value changed. Well, of course, that one is because I chose the wrong side. Let me go to greater than. Okay, so that's still a reject. Actually, let me go back to not equal. Right now, because the p-value is less than 0.05, we're rejecting the null hypothesis. So you have a nice clear red. You have the p-value in red, as we've always have had that. But now, in addition, you can see the red and the green. Now, again, on the alternative hypothesis, you're not proving the alternative hypothesis, but you can say it's true. You're accepting it at the 95% confidence level. So a reject is strong. A fail to reject, however, is weak. So on a fail to reject, that was actually, let me just change this to, let's say, 0.9. So when I do a fail to reject, I put it in light green because, as everybody knows, or I hope everybody knows, fail to reject does not mean that you've proven the null hypothesis to be true. So we shade it just a light green. There's insufficient evidence to reject the null hypothesis, but at least with the color coding, it just makes it a little bit easier to interpret the outcome of the p-values. We have the statistical calculations as usual, and then we include the confidence intervals here. So pretty straightforward. Really, the main additions or the main changes versus what we had in the older template is now the drop-down menu where you specify the alternative plus the display of test information. We've always had the that note on interpretation. For confidence intervals, we've also added a note for the interpretation of the p-value. Okay, so that's the Onesample Ttest. Let's look at the Twosample T. Like I said, I'm just gonna kind of quickly go through this. Basically, the Twosample T is the same. Obviously, you put your summary statistics in for sample 1 and sample 2. And you put in your hypothesized difference, and again, as per the previous template, you have your less than, not equal to, and greater than. And the other thing is, before we used to have two separate templates, one for assume equal variances and a different template for assume unequal variances. Now you can just select and you'll get the updated, it'll just do the calculations appropriately. There is another thing that I want to mention, that's kind of a technical note. In Excel 2010, Microsoft dramatically improved the quality or the algorithms for the various statistical functions. Now, we could have built these templates based on Excel 2010 and higher, but what we did was we put in a detection, and the version of Excel that is being used and then apply the appropriate formulas. So if it's the newer formulas, we use the newer formulas to get more statistical precision. If it's a 2007 and below, then we use the older formulas. Okay, so it's backwards compatible, but also takes advantage of the new functions that Microsoft has put out. Okay, so that's the Twosample, and now I will, let's open up the standard dev. So the Onesample chi-square test, in the previous version, we did not include the, we only included the confidence interval. We did not have the hypothesis test. So now we have the confidence interval on the standard deviation as well as the hypothesis test. So you get both the, you can specify not equal to, less than, or greater than. You can specify a hypothesized value, and you get your p-value. So we've added, in all of the templates, you're getting both the hypothesis test and the confidence interval. Okay, so that's the Onesample standard deviation. And the Twosample Ttest, same thing. Actually, in the old version, we only had the test. We did not include the confidence interval. So here, you're getting both the test and the confidence interval. So this is again, this is the F-test. So this one assumes normality. Okay, so you're plugging in the sample size and the sample standard deviation, again, the alternative hypothesis. And the null hypothesis is the hypothesized ratio of standard deviations. Okay, so that's what you put in as your null hypothesis, or your hypothesized value. Okay, so that's the Twosample F-test. Again, both the hypothesis test and the confidence interval, as well also support for the new Excel 2010 functions. Okay, the next one that we're going to do is we're going to one proportion test. In the old one, we only had the confidence interval, and the confidence interval was the exact confidence interval, and we also had the normal approximation. Those values were reported. Now, okay, let me just cover a few things here, because there's a few things that have been added, and so we have the hypothesis test method. Let me start with that. Under the hypothesis test method, you have two choices, binomial exact and normal approximation. So normal approximation is really not recommended. You should use the exact method for hypothesis testing, but sometimes if you're doing hand calculations and you want to validate your hand calculations, then you can apply the normal approximation to just confirm that your hand calculations are correct. So, for example, in a training situation, you might want to use the normal approximation and confirm that you did the calculations correctly. However, it's always better to use the binomial exact. Problem is the normal approximation numbers are not going to be correct, especially dealing with small proportions. As you approach 0 or you approach 100%, the normal approximation values are not going to be very accurate. So you really do want to use the binomial exact. And the same is true for those confidence intervals. Now, the confidence intervals, you have a couple of choices. And one of them is the exact method. The other is Wilson. And then you have the normal approximation. So here's the thing. If you have a situation where you need conservative confidence intervals, that is, it's something that you have to have strict coverage, guaranteed 95%, then you can go ahead and use the exact. However, if you only need an average 95% coverage, then you're better off using the Wilson score, because, as I mentioned earlier, because you have that oscillation problem, the Wilson score gives a narrower interval, and so is really a better, more practical confidence interval. We have, for completeness, because some people prefer there's another alternative to Wilson called the Jeffreys, and I'm not really recommending the Jeffreys, but it's in there because some people like to use it, and in some papers, Jeffreys is recommended for one-sided test over the Wilson score But for practical purposes, I would say if you do not need to be ultra-conservative on the confidence intervals, then use the Wilson score. If, on the other hand, you really do need a conservative confidence interval, but understand that it's going to be wider, then you go with the exact. Okay, so that's the confidence intervals and the hypothesis test for one proportion. And I do have a question. Is it possible to graphically show the tails? And no, in these templates, we do not have a graphical representation. All right, so that's the one proportion test. So these numbers, basically these example numbers are they're just example numbers. You can change them. So the next template are the two proportions. And in the two proportions case, we have hypothesis test method, Fisher's exact. Previously, by the way, we only included the hypothesis test. We did not include the confidence interval. So you have Fisher's exact, you have normal unpooled, and you have normal pooled. Again, on the normal side, really only recommended when you're doing hand calculations. Fisher's exact is a better method for the hypothesis test to get the p-value. And if the null hypothesis is different, then you should use the unpooled. Okay, so typically you would leave this as 0. In other words, you're testing for equality of proportions, as opposed to testing for a specified difference in proportion. Now, confidence intervals. There are exact confidence intervals available for a two proportions test. They are, unfortunately, computationally very intensive, and depending on the sample sizes, you would be sitting there waiting for 30 seconds to a minute for the computer to calculate the confidence interval. And that's really not acceptable in the context of a template. So we do not include exact methods, the ultra-conservative methods. The recommended confidence interval is the Newcomb-Wilson. That gives, on average, a 95%. And there is something called a continuity corrected, is more conservative. So what I would suggest is if you were needing a more conservative confidence interval, you could go with the continuity corrected. But if you just want 95% on average, then go with the Newcomb-Wilson. Newcomb-Wilson score continuity corrected is not considered an exact method because it does not guarantee 95% under all conditions, but it's definitely more conservative than the regular score method. Jeffreys Perks is, some people prefer that, so we've included that as an option. So practitioners may already be using the Jeffreys Perks confidence interval for two proportions, so we've added that. However, the recommended is the first one, the Newcomb-Wilson score, and that gives you your 95% or whatever confidence level you dial up. Now, the Poisson rate is kind of similar to the one proportion, two proportion, but the difference is that the one is based on binomial, the other is based on Poisson. And so when you have an area of opportunity, one thing, for example, now a proportion is constrained from 0 to 1. Whereas a Poisson rate, you can have a sample size. I can have, for example, I observe 10 defects, a sample size of 1. All right. So the occurrences per sample size can exceed 1. It cannot be less than 0, but the rate value can be any positive number. And so we have the hypothesis test. We have again the Poisson exact versus the normal approximation, and then the confidence interval. Same issues apply as with the proportions. You have the exact test, which is strictly conservative, guarantees the 95% coverage. But if you only need 95% on average, then use the Jeffreys confidence interval. And we would recommend the use of the Jeffreys confidence interval because you're going to have narrower intervals to deal with just your more typical situation. Remember, in order to guarantee 95% under all conditions, the intervals are necessarily going to be wider. And the only reason we include the normal approximation is really to validate hand calculations. So if I go to basic statistical templates, two Poisson rates, there is no exact method. So basically you have a Jeffreys hybrid and a normal approximation. So we have the same similar situation in terms of computational difficulty with an exact method when it comes to the two samples. So it's just much easier within a template to include a methodology that gives you 95% coverage on average. The last template is the one-way chi-square goodness of fit test. So on the one-way chi-square goodness of fit test, these are different categories. So a category ID could be, so for example, number of people born in January versus February versus March, or location 1, location 2, location 3. So it's a discrete category, and you have different observed counts, where the question is, are there any statistically significant differences on the count data across different categories? And so we've added that, and you can actually click the button to show calculations, and this shows you the intermediate calculations with the contribution to chi-square. And so that one thing that also I'll mention is that it does tell you the percentage of cells with expected count less than 5. You have what you want to have is you want to have no more than 20% of the cells have an expected count less than 5 in order for the p-value to be valid. So this is actually too high of a number. All right, so for example now, if I increase this to say 3, okay, so this would actually be an example where now you're meeting you're meeting that 20% rule. So really, you want no more than 20% of the cells to have an expected count of less than 5. And here are the expected counts. So you can look at those as well. Okay. So again, I'm not going to get into all the technical details, but I'm just simply highlighting the various templates and the the practical application here. So in any situation, like for example, if you were rolling a dice, you had 6-sided dice, and you would indicate you roll that dice 100 times, and you recorded how many 1s and how many 2s, how many 3s, how many 4s, 5s, 6s. You would expect this p-value to be greater than 0.05. But if it was a loaded die, and you were to roll a loaded die, then you might get, let's just say, I'll just throw some numbers down here, but you might get a 2, or let's say we want, okay, let's say, yeah, something like this. You might get 20, and let's say, let's make that even 30. Okay, so in a case like that, you have statistically more 6s than you have 1s, and that would show up as a low p-value. So you would reject the null hypothesis. All of the observed counts are equal across groups. So that actually concludes the coverage of the template. So what I want to do now is I want to go back to the questions. And Prasad, you had a question specific to the two proportions. So let me pull that back up. So two proportions, and you had 3 out of 21 and 6 out of 19. Okay. So what this is a fail to reject. You can see the p-value is bigger than 0.05. It's a fail to reject. And so what we have to do is we would conclude that we cannot say that these two proportions are different. All right. Doesn't mean we've proven that they're the same. Like this is, I know it looks like a lot. It's maybe that Prasad, that was the question. It looks kind of weird here, 14% versus 31 or 32%. But that's the whole point of using the calculator, because when you're dealing with discrete data, you really need large sample sizes to have sufficient power to detect a difference. Okay, and that's even though it's 14% versus 32%, because the sample sizes are so small. In a discrete case, 20 is not a large sample size. Remember, it's not the same as a t-test, where 30 is a good number. In a proportions case, with sample sizes of 20-ish, you need a very large difference before you can conclude that they are significantly different. But keeping in mind the understanding, this light green doesn't mean that I have proven that these two samples have equal proportions. I just don't have a large enough sample size to conclude that they are different. That's always the problem with the null hypothesis. You never prove the null hypothesis. A fail to reject simply means there was insufficient evidence to reject the null hypothesis. Like in a court of law, the defendant is innocent until proven guilty, and the job of the jury is to see if there is evidence beyond any reasonable doubt to find the defendant to be guilty. So a statistical test is much like the verdict in a court of law, and you need strong evidence. Okay, so with that, I thank you very much for attending, and we thank you for your enthusiasm and support of SigmaXL, and we really strive to make this a better product. We want to practice what we preach. So your feedback is greatly appreciated, feature requests. So thank you all very much. Have a great day.